तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Last two classes we were discussing about advanced wastewater treatment. We have seen the membrane processes as well as adsorption in detail. Yesterday we started with ion exchange process. Today we will continue on that. We will be discussing about ion exchange processes and other advanced wastewater treatment like advanced oxidation, distillation. Then we will start the theory or what is the theory of industrial wastewater treatment. Okay, so those things we will discuss in today's class. So first we will see what is ion exchange. This we have discussed yesterday. Ion exchange is defined as the process where an insoluble substance remove ions of positive or negative charge from an electrolytic solution and releases other ions of the same charge into the solution in a chemically equivalent amount. That means here exchange of ions will be taking place. So one type of ions will be getting removed from the solution, but equal amount or equivalent amount of ions will be coming from the resin. Okay, so that is why it is known as an ion exchange process, and the resin there will not be any structural change, and the ions whatever is present in the solution it will be diffusing into the ion matrix. So if you want to write the equation of an ion exchange reaction, we can write like this: Nr into A plus plus B N plus. So this is the ion of interest in the solution we have to remove, and this is the ion exchange resin, and R is the anionic group attached to the ion exchange resin, and A is the cation which is attached to the anionic group. And if ion exchange has to be taken place, so this B N plus 1 should have more preference to this anionic group compared to A plus. So what will happen? This B N plus will replace A plus. So the charge neutralization should be there because this B is having N plus positive charge. So instead of maintaining the charge neutralization, so what should happen? N ions of A plus should come out. So that is what is written here: Rn minus into B N plus plus N into A plus. So if you want to find out what is the selectivity coefficient or how much selectivity this B ion is having over A ion on the ion exchange resin, then we can see, we can calculate that one using this expression. So K Bn plus 1 over A plus, that means selectivity of B over A, selectivity coefficient of Bn plus ion over A is equal to Rn minus 1 Bn plus 1, its concentration in the resin, into A plus raised to N, because N ions are coming out in the solution, divided by Ra plus 1 raised to N, because N Ra plus 1 was involved in the reaction and Bn plus 1 in the solution. So this is the expression to find out the selectivity coefficient. It is just similar to the chemical equilibrium. So how we find out the chemical equilibrium constant? It is nothing but the product of the concentration of the product divided by the product of the concentration of the reactants. So that is exactly what we are doing here. So another term which is commonly used in ion exchange process is selectivity coefficient. So this also we have explained yesterday, or it is also known as separation factor, and usually it is represented as QS. Okay, it is similar to the selectivity coefficient. Only thing is here we are considering only one ion of each cation. So here we are writing like this: Rn minus Bn plus in the resin into A plus in the solution. We are not taking the number of ions into consideration, divided by R A plus in the resin by Bn plus in solution. Or if you want to make a equation which shows the relationship between the selectivity coefficient and selectivity quotient, then we can write like this: selectivity coefficient is equal to Qs into A plus solution by A plus in the resin raised to n minus 1, because 1 is taken care of here and n ions of A plus is involved in the reaction. So, if you multiply this Qs by this ratio raised to n minus 1, then we will be getting the activity coefficient. And if n is equal to 1, Qs and this activity coefficient are identical. So, this Qs is very, very important term, because by seeing the Qs we can make out whether the ion exchange is feasible or possible or not. If Qs is greater than 1, we will be getting line like this, or the ion exchange process can be expressed like this. This is the equivalence of ion fraction in solid phase, and this is the equivalence of ion fraction in liquid phase. So, this shows that more ions are getting concentrated on the solid phase, and if Qs is 1, that means it is a linear variation, and Qs is less than 1, it is unfavorable ion exchange. That means in the cation, whatever is already existing in the ion exchange resin is having more selectivity over the ion whatever is present in the liquid. So, we will take a common example. If you have a resin with sodium ions on that one, and we want to use this resin for the removal of calcium. So, the chemical equation we can write like this: 2R Na plus, because calcium is having a valency of 2 and sodium is having a valency of 1. So, if you want to exchange calcium ions, then definitely there should be 2 molecules of this RNA. So, then only the exchange process can take place. So, that is why the reaction is coming like this. So, 2RNA plus Ca2 plus will gives you R2Ca2 plus 2Na. So, if you want to find out the selectivity coefficient of calcium over sodium, then we can get like this: R2Ca2 plus concentration into Na raised to 2, because 2 ions are coming out, by RNA plus raised to 2, because 2 ions are or 2 molecules are present here, into Ca2 plus. So, if this is greater than 1, that means this ion is having more preference on calcium ions than sodium ions. That means calcium ions can easily be removed from the solution. And now we will see how the affinity of ions for a resin can be generalized, because many different types of ions will be present in the wastewater, especially when we talk about the wastewater coming from the industries. In the process they will be using many different inorganic salts. So, definitely when it is in the solution, different types of cations and anions will be present, and we are interested in removing a particular ion or a group of ions, and we do not want to remove all the ions. So, how can we decide which ion exchange resin can do that one, or which ion will be removed more? So, these are the points which will tell you which is having more affinity. So, ions of high valence are preferred over ions of low valence. This is very, very important. If you have a ion with 3 valency and an ion of 2 valency and an ion of 1 valency, the ion with 3 valence will be preferred over 2 valence, then the single valent ion will be taken up. So, that is what this shows. Fe3 plus will be having more preference over Mg2 plus over Na plus. Similarly, anions also, phosphate, it is having 3 valence, is having more preference over sulfate, and sulfate is having more preference over nitrate, which is a single valent ion. So, this preference increases with a decrease in the total ionic concentration of the solution. So, for example, we have seen that Fe3 plus is having more preference over Na plus, but if Fe3 plus concentration is very, very less compared to Na plus, then what will happen? Because of the concentration gradient, Na plus will be getting attached more. So, this point is also very important. And second one is, for ions of same valence, the extent of the exchange reaction increases with decreasing hydrated radius and increasing atomic number. So, this is also very important. If the valency is the same, then if the ion which is having the less hydrated radius and more atomic number, that will be preferred. For example, if you have calcium, magnesium and beryllium, we know that all these three ions are having a valency of 2 plus. So which will be preferred over the other? So calcium will be having more preference over magnesium, and magnesium will be having more preference on beryllium. Similarly, if you take the case of potassium, sodium and lithium, because lithium is coming first in the periodic table, then sodium, then potassium. So potassium is having high atomic number, so K plus will be preferred over Na, and Na will be preferred over lithium. Similarly, for a solution with high total ionic concentration, in the extent of ion exchange reactions follows no general rule and is often reversed. For example, okay, if you have a single valent ion and a trivalent ion or a divalent ion, okay, from the dilute solutions we can easily remove the divalent ion with the exchange of single valent ion. But if you put another solution which is having very high ionic strength, then what happen? The preference may reverse. So this principle is used for the regeneration of ion exchange resins. For example, if you want to use some resin, especially the zeolite resins and all, for hardness removal, which we have discussed earlier, so the calcium ions and magnesium ions will be getting removed, and once the ion exchange resin is saturated, if you want to regenerate that ion, what we have to do? We have to pour sodium chloride solution with high concentration, that means some 10 to 20% sodium chloride solution. If you pass, then what will happen? The calcium and magnesium ions will be thrown away from the ion exchange resin, and sodium will be occupying the place. So that is what is written here. And the fourth point is the relationship between the degree of cross linking and the size of the hydrated ion may affect the extent of the exchange reaction. If the resin has a high degree of cross linking, the ion may be too large to penetrate into the matrix of the resin. So the cross linking of the matrix of the resin is also very, very important. If the pore space is very small, then what will happen? The ions with large hydrated radius may not be able to penetrate through the pores of the resin or the matrix of the resin. So in that way also we can segregate the ions whichever we want to remove. Now we will see what are the advantages and disadvantages of choosing ion exchange process. The advantages are, it means if you go for a high affinity for the ion to be exchanged, then you will be getting a sharp breakthrough curve, then shorter ion exchange column, because the ions in solution will be having very high preference over the ions whatever is sitting on the resin. So a shorter ion exchange column can remove the ions in the solution, and greater flow rate can be applied in the ion exchange column. So these are the advantages. Okay, if you choose a resin with a high affinity for the ion to be exchanged, sharp breakthrough curve, shorter ion exchange and greater flow rate applied to the ion exchange column. And the disadvantage is higher regenerance concentration is required, because the ion which is exchanged is having very, very high affinity to the resin compared to the ion whatever was already existing that one, or already existing in the resin. So if you want to replace the ions, okay, or if you want to regenerate the resin, then what we have to do? We have to give very high concentration gradient, then only it can push out the ions whatever is exchanged. Now we will see what are the different types of ion exchange resins. The ion exchange resins can be divided into two major categories. One is cation exchange resins and another one is anion exchange resins. The name itself explains what it means. And the cation exchange resin can be divided into two categories. One is strong acid exchange resins and another one is weak acid exchange resins. And in anion exchange resins also there is strong base exchange resins and weak base exchange resins. So once again the classification is, the major classification is cation exchange resin and anion exchange resin. And in cation exchange resin, strong acid exchange resins are there, weak acid exchange resins are there. In anion exchange resins, strong base exchange resins are there and weak base exchange resins are there. Now we will see in detail what is this strong acid exchange resins and weak acid exchange resins. Similarly, what is the strong base exchange resins and weak base exchange resins. A strong acid exchange resin is the one whose functional group is derived from a strong acid. So this is very important. A strong acid exchange resin is the one whose functional group is derived from a strong acid. Their degree of ionization is analogous to that of a strong acid. That means it will be ionizing very fast and which permits the hydrogen to be dissociated and ready for exchange over a wide pH range. And now we will see what is a weak acid base resin. So here the functional group is derived from a weak acid like carboxylic or phenolic acid, and these resins are able to work only in low pH range. So the difference is this is derived from a strong acid and it undergoes ionization very fast and it can function in a wide pH ranges, whereas a weak acid base resin, the functional groups are generated or developed from weak acid like phenolic acid or carboxylic acid, and the major disadvantage is such resins can be functional only in a small pH range below pH 7. I will show you some examples of this strong acid exchange resins and weak acid exchange resins. So this is a strong acid exchange resin RSO3 minus H plus. So this is the anionic group attached to the resin and this is the functional group which is derived from the acid. And if you add a salt NaCl, then what will happen? Okay, this H plus will be replaced by Na. So you will be getting a strong acid HCl and other thing will be RSO3 minus Na plus. Similarly, we can write this one. Okay, if you want to go for the regeneration, what will happen? This is already exchanged with Na plus. You add the strong acid, so it will be again coming back with H plus ions and you will be getting the corresponding salt. Okay, the major disadvantage of this strong acid exchange resin is because it is having high affinity to this one compared to other cations. So the regeneration efficiency will be very less. The maximum regeneration efficiency you can get is 30 to 50%, but it can use for a wide pH range. So this is weak acid exchange resin. So this is an organic acid. So you are adding sodium bicarbonate. So you are getting sodium salt of this one and H2CO3 is coming out. Okay, and similarly the sodium salt, if you can add an acid, then it will be replaced by H plus ions and the salt will be coming. So the advantage of this weak acid exchange resin is the regeneration capacity is very high. The reason is the affinity towards this one because it is functioning as a weak acid. So this affinity will be not so high, so we can easily replace this one. So that is why we are getting a high regeneration efficiency. Similarly, strong base exchange resins which is derived from a strong base. Okay. So that is what is, because it is having a functional group OH. When we add some salt, what will happen? This Na plus will, Cl minus will be replacing this OH and you will be getting the corresponding base. And if you add HCl, Cl and H2O, and here again the regeneration efficiency is very less. You will be getting a regeneration efficiency of 30 to 50%. And weak base exchange resin, just like weak acid exchange resins, okay, regeneration we will be getting 100% and pH value, it will be functional only pH value less than 7. Okay, so these are the different types of ion exchange resins. Now we will see what are the general characteristics of an ion exchange resin. So whenever we want to go for an ion exchange process, we should know what is the general property or what type of resin we have to select and what is the quantity we need to treat the effluent or to get the required treatment efficiency. So the most important parameter is the ion exchange capacity. So now we will see what is this ion exchange capacity. It is nothing but the total capacity. The ion exchange capacity is a measure of the total quantity of the ions which theoretically can be exchanged. That means it is nothing but the number of ionizable groups that is present in the ion exchange resin per unit mass or per unit volume of resin. Okay, usually it is expressed as milliequivalents per liter or milliequivalents per gram. That means what is the maximum number of ions the ion exchange resin can exchange. That means it is nothing but what is the total ionizable group present in the ion exchange resin. So if the number of ionizable group is more, then what will happen? that much of ions can be exchanged for some other ions whatever is present in the wastewater. So, this ionizable groups or the amount of ionizable ions present in the ion exchange resin will give you the ion exchange capacity, and the unit usually used is milliequivalents per liter if you want to express it in terms of volume, or milliequivalents per gram if you want to express in terms of weight. Now we will see, okay, that is the total capacity. If you want to find out the operating capacity is a measure of the actual useful capacity of the resin for exchanging ions from a solution flowing through a fixed bed of resin particles under specified conditions. So, once again, the operation or operating capacity is a measure of the actual useful capacity of the resin for exchanging ions from a solution flowing through a fixed bed of resin particles under specified conditions. So, this is very important because we know what is the total exchangeable capacity or total ion exchange capacity of the resin, because we know what is the exchangeable groups present in the ion exchange resin. But when we use this ion exchange resin in the treatment of wastewaters, what will happen? All the ionizable groups may not be exchanging, and depending upon the wastewater conditions and the operating conditions, the exchange capacity will be varying. So, the theoretical capacity and the actual capacity will be different. So, how can we find out the actual capacity? What we have to do? We should know what is the total amount of ions we are passing through the column, and we should know what is the ions whatever is coming out from the column. So, if you take the difference between these two parameters, then we will be able to get what is the operating capacity. So, that is what I have written here. Operating capacity can be represented by the term X. It is equal to number of equivalents of the ions of interest applied to the column per resin volume minus number of equivalents of the ions of interest passing through the column per resin volume. That means we know what is the total amount passed through the column and whatever is coming out of the column. So, rest of the ions will be taken up by the column. That means that is the operating capacity. So, now how can we use this ion exchange resins for treating the wastewater? So, we can go for 4 different modes of operation. One is batch mode, and another one is fixed bed mode, third one is fluidized bed, and fourth one is continuous mode. So, we have already discussed all these things. Okay, we will see once again. So, batch mode means you will be taking the wastewater, putting the ion exchange resin and give some time for reaction, and afterwards remove the supernatant. So, that is a batch mode. Fixed bed, that means you will be having a fixed bed, through that one you are allowing the wastewater to flow, then you will be getting the treated water. And in fluidized bed, what is happening? The ion exchange resin will be present in a reactor, and because of the wastewater flow velocity, it will be in a fluidized form, and because of that one, the waste components will be having good contact with the ion exchange resin, and ion exchange will be taking place. This fluidized bed and all we have discussed in detail when we were discussing about anaerobic processes. And continuous process, this is the most commonly used operational mode. Okay. So, in continuous process, okay, if you want to operate an ion exchange resin, okay, we can classify the operation into 4 categories. One is the service time, second one is the backwash time, then regeneration, then fourth one is rinse. Service is the time when the pollutants are getting removed from the system, and backwash means we are using this backwash to remove any turbid particles whatever is getting attached to the fixed bed column, and regeneration we are removing the exchanged ions with the initial ions, and rinse. So, some loose ions will be present in the column. So, if you want to remove that one, we are going for rinse. So, I will explain this ones in. Okay, so if you want to use the ion exchange resin for the removal of sodium chloride, okay, for desalination purpose, if you want to use that one, so what we can do, we can go for a strong acid cation exchange resin, and in the hydrogen form is used. So, this is RH plus, okay, strong cation exchange resin, and if NaCl is there, what will happen? RNA will be forming and H plus will be coming out, and if you want to find out the selectivity coefficient, we can find out using this expression. And the resin, whenever we go for a single stage resin, we have to use more resin compared to a multi-stage process. So, this is okay. If you want to plot X B over R, that means the selectivity coefficient of B, the ion to be exchanged from the polluted water over the ion of the resin, and here we are putting X, okay, of B in solution. So, or what is the concentration of B in the resin, and this is the concentration of B in the solution. So, if you get a graph like this or a trend like this, this is a preferable ion exchange. That means at any time the concentration of the B, concentration of B ions, okay, which is of interest to us, which has to be removed from the solution. If this concentration is high on the resin compared to the concentration of B on the solution, that means the ions are getting exchanged at a faster rate. So, this is a preferable ion exchange, and if you get in this way, that means the concentration of B in solution is more compared to the concentration of B on resin, then it is a unpreferable ion exchange. That means resin ion is having more attachment than the ion B which is present in the solution. So, in this process we cannot go for ion exchange. So, now we will see how the backwashing, because operation period we know that, okay, depending upon the ion we have to select the resin, and which cycle it has to run, that also we have to decide. Then we can find out whether ion exchange is feasible or non feasible, then we can select the process. Once the capacity of the resin is over, first we have to go for backwashing. So, backwashing is employed after the operating capacity of the ion exchange is reached or the capacity is exhausted. So, how to do the backwashing? So, first we have to break up the resin clumps, remove the finely divided suspended material in the resin by filtration, and eliminate the gas pockets, restart the resin bed and ensure a uniform distribution of flow during the downflow operation. So, these are the things whatever is happening in a backwashing. Now, we will see what is happening in regeneration. It replaces ions exchanged during the service run and returns the resin to its critical exchange capacity or to any derived level depending upon the amount of regenerant use. Okay. In other words, regeneration, what they are doing is, it is replacing the exchanged ions and bringing back the ion exchange resin to its original capacity, or sometimes what will happen, for example, the strong cation exchange resin, strong acid cation resins, what will happen? We will not be getting 100% regeneration efficiency. So, you will be getting only 30 to 50%. So, regeneration will be increasing or replacing the ions whatever is exchanged to the resin up to 50%. That is the maximum possible limit. But if it is a weak exchange resin, then we can go for, or we will be achieving 100% efficiency. So, that is what is happening in regeneration. And if you want to calculate the regeneration efficiency, it is nothing but the ratio of the total equivalence of ions removed from a resin to the total equivalence of ions present in the volume of regenerant used. So, this is the regeneration efficiency. So, if you know what is the equivalence of ions present in the resin, and we know what is the equivalence of ions present in the regenerant solution. So, we will be taking the ratio of these two, and that will give you the efficiency. So, if it is having 100% efficiency, so it should replace whatever is the equivalence of ions present in the resin by the equivalence of ions present in the regenerant solution. If the efficiency is not 100%, only a fraction will be getting replaced. And regeneration level is the extent of regeneration. And selectivity coefficient of ion exchange resin, okay, this plays an important role in regeneration. Strong resins, it is having a higher selectivity coefficient. So, what will happen for the removal? It will be very good, but for regeneration what will happen? The exchanged ion will be having more preference over the ions whatever is present already in the resin. So, in regeneration the exchange will not be proper or regeneration efficiency will not be high, but in case of weak resins what will happen? It will be having high affinity to the initial ions whatever is present in the resin. So, it will be having a high regeneration efficiency. So, selectivity coefficient if it is high, removal is easy but regeneration is difficult. If selectivity coefficient is less, removal is difficult but regeneration is easy. And the last step is rinsing. It is to displace regenerant and the waste from the resin, okay. And because after the regeneration what will happen, some of the loose ions will be sitting on the resin column. So, if you want to remove that one, what will happen? The next cycle or the service run, those ions will be coming out along with the treated water. So, it is not preferable. So, the rinse is meant to remove whatever is the loosely attached ions present in the ion exchange column. And in operating mode, we can either go for counter current mode or co-current mode. In counter current mode, what is happening? Operation in one direction and regeneration in opposite direction. In co-current ion exchange, both operation and regeneration are performed in the same direction. So, that is the difference between a counter current mode and a co-current mode. So, now we will see what are the applications of ion exchange process. It is used for the removal of colors because color is a very common problem in most of the industries and it is very difficult to remove the color effectively. And unlike other pollutants, the color is having other problem even though the concentration is very less. What will happen? A slight amount of the color will be visible. So, the public will be having a feeling that the industry is not going for proper treatment. So, color removal is very important and this ion exchange resin can be used for that purpose. And another one is hardness removal. This we have seen in detail when we were discussing about softening. And another one is removal of dissolved solids and nutrients from water like nitrate and phosphate. So, for that one also anion exchange resins can be used effectively. Then for the removal of heavy metals, okay. For this also we can use the ion exchange resins effectively. Now, we will see the other advanced wastewater treatment process, that is nothing but advanced oxidation process. Here what we are doing is we are using some strong oxidizing agent, non-conventional oxidizing agents. So, it is having such a high oxidizing capacity. So, whatever is the pollutant whichever is present in your system, especially the non-degradable organic toxic compounds. So, such cases we can go for this advanced oxidation process. So, what will happen? These oxidizing agents that will be reacting with the organic pollutants which is non-biodegradable and convert it into some other forms which is non-toxic, or sometimes what they will do, they will be converting it into carbon dioxide, water and other inorganic substance which is environmental friendly. So, that is what is happening in advanced oxidation process. So, it is to oxidize complex organic constituents to simpler end products, okay, because we know that all the organic compounds are non-biodegradable and some of the toxic compounds, persistent toxic compounds are complex organic compounds. So, in such cases we can go for this advanced oxidation. And here if different terms are there, we will see what are the important terms coming under this advanced oxidation process. First one is primary degradation. Okay, primary degradation is a structural change in the parent compound. Okay, when it undergoes some oxidation, okay, it need not be complete oxidation. So, only some structural changes are taking place in the complex organic compound, that is known as primary degradation. And the other term is acceptable degradation. In acceptable degradation, what is happening? Structural change in the parent compound is taking place, and because of the structural change, the toxicity of the compound is reduced, that is known as acceptable degradation. And the another term is ultimate degradation. So, it is ultimate degradation means complete oxidation is taking place. So, the complex organic matter is getting converted to carbon dioxide and water, and in sometimes what will happen because of this oxidation, okay, that is termed as unacceptable degradation. Okay, a structural change in the parent compound can take place which result increased toxicity. So we have seen what is primary degradation, acceptable degradation, ultimate degradation and unacceptable degradation. So we are only interested in acceptable degradation or ultimate degradation. Okay, for example, endosulfan is a pesticide. Okay, it is very commonly used in India. So if you go for this advanced oxidation, okay, either it can get converted to carbon dioxide, water and nitrogen. Okay, so sometimes what will happen, some other compounds like endosulfan sulfate or endosulfan diol can form. Okay, this endosulfan sulfate is much more toxic than the endosulfan itself. So that is known as unacceptable degradation. Okay, just an example I am giving this. Now we will see what are the oxidizing agent commonly used for this advanced oxidation. So this table shows you the compound and its electrochemical oxidation potential. The higher the electrochemical oxidation potential, the more active the compound is. So fluorine is having an electrochemical oxidation potential of 3.06 and hydroxyl radical OH radical is having 2.8, and this is the nascent oxygen, it is having 2.42, and this is ozone, it is having 2.08, and hydrogen peroxide is having 1.78, HOCl is having 1.47 and ClO2 is having 1.27 and oxygen is having 1.23. But in usual chemical oxidation, okay, we are using oxygen or any other oxidizing agent, but in advanced oxidation process, the oxidizing agents used are having very high electrochemical oxidation potential compared to oxygen. So their oxidation potential will be so high, the oxidation reaction will be very fast. The last one coming under the advanced wastewater treatment is distillation. So this we all know what is distillation. So what we do, we boil the water and take the vapor and condense it and get the pure water. So that is the distillation. So we will see how a distillation unit is functioning. So it is having, this is the wastewater to be demineralized. Okay, it is entering here, and what is happening, this is a heat exchanger. So when it passes through this one, it will be evaporating, okay, and the vapor will be going through this one. Okay, this is the condenser tube, and the concentrated waste is coming here, and this is the heat exchanger. That means, okay, the heat exchanger and the temperature will be recovered, or the temperature of the wastewater stream will be recovered, or temperature will be reduced and the heat energy will be recovered, and the concentrated waste is going out here, and some of the waste, whatever the cooled waste, it will be used here to condense the vapor whatever is coming here, and this is the, okay, this is the vapor and this is the vapor pump. It is going through this condenser tubes and condense, and we will be getting product water. Okay, so what we are doing, taking the wastewater, boiling it, and we will be getting the steam. Okay, and here the concentrated waste is going out, and whatever the water which is cool, it will be used for cooling down the vapor, and the condensed vapor we will be collecting as the product water. So that is a distillation unit. So it is a unit operation in which the components of a liquid solution are separated by vaporization and condensation. Okay, so this is distillation. And application, when high degree of treatment is required and contaminant cannot be removed by other means, and the third one is if inexpensive heat is available. So this method is used to, if you have brackish water or salt water, if you want to get good water for drinking purpose, you can go for this distillation. So we can make, okay, homely household unit for this distillation purpose, or for cleaning the brackish water and get the clean water for drinking water. So there we are using the heat energy from the sun. Okay, so what you have to do is take a bottle okay, boil the water, okay, and collect the vapors, okay, and allow it to condense, okay, and the sunlight, whatever is the energy coming from the sunlight can be used for the distillation purpose, okay. This is practiced in some houses where they don't have any pure water for drinking, okay. And distillation process can be done in various ways, either by using boiling with submerged tube heating surfaces, or boiling with long tube vertical evaporators, or flash evaporation, or forced circulation with vapor compression, or solar evaporation. This is what I was explaining, okay. This is a low cost technology, and we can go for rotating surface evaporation, or wiped surface evaporation, or vapor reheating process, direct heat transfer using immiscible liquids, or condensing vapor heat transfer. Okay, there are many ways we can use this distillation process to clarify the water, but the only problem is this process is very costly. So if you don't have any other treatment option, then only we can go for this distillation process. And the other one is, if you can get inexpensive heat energy, then we can go for this distillation. And most of you must have seen the distillation units, isn't it? In laboratory purpose, we use distilled water for making the chemical solutions and all. So how you get the distilled water? So we are having a distillation unit. So it is working in the same principle. Now, till now we were discussing about advanced wastewater treatment processes, including membrane processes, adsorption, ion exchange, advanced oxidation reduction, then distillation. So why we wanted to use this one? Because we know that in the conventional wastewater treatment, okay, basically those things were derived for treating the domestic wastewater, which is having lot of biodegradable organic matter. But nowadays, so many non-conventional pollutants and emerging pollutants are coming along with the wastewater. Where are these non-conventional and emerging pollutants are coming from? Mostly it is because of the industrial activities. So whatever the advanced wastewater treatment processes we have discussed, all these processes can be used for industrial wastewater treatment depending upon the pollutant nature, okay. So if you want to go for the selection of a process, what we have to do? We will be having the industrial wastewater, and first we have to characterize the wastewater, or we have to find out what is the characteristics of that wastewater. Then if you see that it is having lot of chemical oxygen demand, that means it is having lot of organic matter. It does not mean that it is all the organic matter present in the system is biodegradable. So how can we choose whether we have to go for a biological system, whatever we have seen in detail, or we have to go for some physico-chemical treatment processes or these advanced treatment processes. So for that one, we have to do some treatment study or treatability studies. Treatability study will tell you, okay, which treatment is suitable for the wastewater treatment. For example, if you have a high COD wastewater and we want to find out whether it is biodegradable or not biodegradable. So what you can do, you can go and find out what is the biochemical oxygen demand of that wastewater. So if you get a high biochemical oxygen demand and you have a high COD, so you take the BOD by COD ratio. If the BOD by COD ratio, that means biochemical oxygen demand divided by the chemical oxygen demand ratio is more than 0.5, that means more than 50% of the waste is biodegradable, then it is advisable to go for a biological treatment first, then followed by some physico-chemical treatment or advanced wastewater treatment, okay. But the BOD itself will not be telling you whether it is completely biodegradable, because what is happening when we do the BOD test for any industrial wastewater, what we do, we take the industrial wastewater and we will be diluting it with the dilution water along with the nutrients and all. So the industrial wastewater, what will happen, it will be having lot of other toxic chemicals and toxic metals along with the organic matter, but when we dilute it, the toxic effect of that compounds will be coming down. So you may be getting a high biochemical oxygen demand, but in actual practice the dilution is not taking place. So, you may not be able to achieve that much of biodegradation in the treatment plants. So, that is why after measuring the BOD by COD ratio, we have to go for a treatability study. So, what you do is take the actual waste and conduct the biodegradation studies, and if the biodegradation is happening or if you can achieve the COD reduction above 50% by the biological means, then in the field also we can practice the same thing. But if the lab itself it is failing, then definitely in the field you will be getting much less efficiency. So, these points has to be kept in mind whenever we decide any process for any industry, especially industry, because municipal wastewater treatment we will not be having any problem, because we know that the most important pollutant or the most important pollutant whatever is present in the domestic wastewater is nothing but organic matter, and most of them are easily biodegradable. Along with the organic wastewater, some of the non-conventional and emerging pollutants will be coming. So, their concentration will be less compared to whatever is coming in industrial wastewater. So, before going for any treatment process, it is advisable to have a treatability study in the laboratory and see how the system is performing, then you scale up and put it in the field. So, now we will see what are the other important points we have to consider when we go for this industrial wastewater treatment. So, what is the effect of industrial wastewater on streams? Because whenever we talk about the industry, especially the public will be telling, oh, if some industry is going to come, it is going to pollute the streams, it is going to pollute the environment, it is going to pollute the atmosphere. So, why the public is having that type of a feeling? Okay, we will see that in detail, and what are the important points, okay, in terms of pollution control the industry has to be taken into account. Okay. So, if the industry is discharge the wastewater, okay, it will be polluting the river, and it will become unacceptable for its best use. So, that will be happening if you discharge any waste to any water sources. So, that is why we were telling that it is always advisable to go for water reuse than the effluent discharge, that we have discussed in detail in the earlier classes. Now, we will see when we talk about the industry, what are the different sources which can generate the pollution in an industry. The sources of industrial pollution are, first one is the extraction and transporting virgin, renewable and non-renewable raw materials. This is the first source of industrial pollution, because for example, if you take any metallurgy industry, what will happen? They have to extract the ores from earth core, okay, and during the extraction process itself what all things will be happening. So, some ore will be left over there and leaching will be there, and the leachate will be contaminating the water courses downstream side, and the leachate will be percolating through the soil and it will be contaminating the soil, and during transport also so much of this raw material will be spilling over and that will be polluting the way. So, all those things are coming under this category, the extraction and transporting virgin, renewable and non-renewable raw materials. Second one is process pollution originating from the production. So, this is not required to be, okay, no need of explaining this point. The reason is all of us know, okay, the industrial process, okay, it will be involving various reactions, various raw materials and various products. So, as a result what will happen? These things will be coming along with the effluent whatever is coming out of the industry. So, definitely the process and the raw materials whatever is used in the industry, okay, that will be polluting. And third one is product pollution. It is nothing but the pollution generated by the everyday use of the products. So, for example, pesticide is an industrial product. So, if you use the pesticide daily, okay, what will happen? When you apply the pesticide, okay, it is killing the pests or it is destroying the pests, that is the positive side of the pesticide. But what will happen? Some amount will be going to the atmosphere by volatilization and something will be sticking on the plants. So, when we take the plant parts or either fruits or the leaves or the stem for our food purpose or eating purpose, then that will be coming into our body, and during the spraying, okay, some portion will be going to the soil, and if precipitation or rainfall comes, what will happen, whatever is there in the soil, a part will be coming along with the run of water, and sometimes what will happen during the rain, some water will be percolating through the ground and it will be reaching the groundwater. So in all the ways it will be polluting groundwater, surface water, soil and the atmosphere. So that is meant by the product pollution. And the last one is residual pollution. Okay, this residual pollution is nothing but the disposal of products. So if you have something left over, okay, the same case we can take the pesticide. Okay, you will be using the pesticide for agricultural purpose or controlling the pest in the houses. So some portion of the pesticide will be left over in the bottles, and after some time what will happen, the expiry date will be over and it will become useless. So what we usually do, just throw it away to the water streams, or you put it in the dustbin, definitely it will be going through different hands and finally reaching either to the soil or the water. So that also will be creating lot of pollutant. So these are the major sources of industrial pollution. One is the extraction and transportation of raw materials, second one is the production itself, third one is the use of the products, fourth one is the residual pollution, that means the discarding process. Now we will see what are the materials which are responsible for this industrial pollution. So we can classify them into these groups: inorganic salts, acids and alkalis, organic matter, suspended solids, floating solids and liquids, heated water, color, toxic chemicals, microorganisms, foam producing matter. We all know from where all these pollutants are originating. Inorganic salts, we know that most of the industrial process use lot of chemicals for their product formation or whatever be the thing, especially the chemical industries. So whatever the leftover salts used in the process, that will be coming along with the wastewater. So definitely the wastewater from the industries will be containing lot of inorganic salts, and acids and alkalis are also being used in industrial process. For example, if you take the electrochemical industry, so for removing the rust or for the pickling process we will be using lot of acid. So what will happen, that acid will be coming along with the wastewater from the industry. Similarly, organic matter depending upon the industry. For example, if you take the case of tannery, lot of organic matter will be coming, and similarly textile industry also lot of organic matter will be coming, distillery industry lot of organic matter will be coming, and other one is suspended solids, because depending upon the raw material the industrial effluent will be having lot of suspended solids, and floating solids and liquids definitely it will be coming from the industrial process, and heated water, this is coming out of the coolers, because most of the cases the industry need lot of cooling water, because so much of heat is generated in the industrial process. So if you want to cool it, then we have to use the cooling water. So after the cooling, what will happen, the water temperature will be increasing and heated water will be coming out. And next one is color. If you take the case of textile industry, we know how much different types of colors, organic and inorganic or synthetic and natural colors are used for the textile industry. Not only in textile industry, other industries are also using many dyes and pigments for their processes. So color is an important component of industrial wastewater. Other one is toxic chemicals like heavy metals, etc., or cyanide. Okay, so these are very commonly found toxic compounds in industrial wastewater. And another one is microorganisms. Whenever we talk about food and pharmaceutical industries, these microorganisms are present in large quantities. So we have to take care of that one also. Another one is from foam producing matter. So these are the materials responsible for pollution in industry. So whenever we design any treatment process, okay, we have to be, now the process should be able to take care of each of these pollutants. Okay. So, most of the time one process alone may not be possible to take care of all these components, then we may have to go for a battery of processes, so that we will be getting the treated water which is meeting the effluent discharge standards. Now, we will see what is the major difference between the industrial and municipal waste. Difference between industry and the municipality is, industry's major objective is to produce the best possible product at the lowest possible cost, because they have to survive in the market. So, if their product cost increases, definitely the cost of their product will be more, and definitely the customers will be looking for a product of the same quality which can be available at a low cost. So, the major objective of the industry is to produce the best possible product at the lowest possible cost. So, if the industry wanted to reduce the cost of production, the most obvious area of cost reduction is nothing but the wastewater treatment. Okay, because if they go for the wastewater treatment, it is not going to add anything to their product. So, they definitely they will be having a feeling that if they want to treat the wastewater properly, they can reduce the cost of the product, because if you go for the wastewater treatment also, that cost also will be coming into the product. Okay. And another important thing is, the industrial operation schedule is extremely variable compared to the municipalities. Okay. And industry view that the wastewater treatment is an imposed necessity on them, and we have already seen that they are pollutants. Okay. Many different contaminants are present at different concentrations, whereas in municipality or municipal wastewater, it will be the organic waste. So, whenever we talk about the industrial wastewater management, we should keep all these points in mind. So, what we will do is, we will discuss these aspects in detail in the next class. Okay, what all are the theory or what all are the things we can follow, so that the industrial pollution can be minimized, because there is no point in going on polluting and treating. So, if we can control the pollution in the source itself, that is the best strategy than initially polluting and controlling the pollution, because we know that pollution is nothing but the resource out of its place. Okay, as far as the industry is concerned, because if more pollution is there, that means more resource or more raw materials are getting wasted. So, that approach we will be discussing in detail in the next class. So, today we will see what all the things we have seen till now. We have discussed in detail about the ion exchange process, and we have seen what are the different types of ion exchange resins we can use, and we have also seen what are the different ways we can put up the reactors for this ion exchange process. Those are batch mode, fixed bed mode, then we can go for fluidized bed reactors, and we can even go for continuous mode systems. And the 4 operating stages are, one is the service time, second one is the backwashing, third one is the regeneration, and fourth one is the rinse period. Okay. So, these 4 operations are associated with the ion exchange. Now, afterwards we discussed about the advanced oxidation process. Here we are using very strong oxidizing agents for the oxidation of complex organic compounds, and we are looking for either complete oxidation or acceptable oxidation. And we also discussed about distillation, and we have seen that this process is a costly process, and if no other process is available, then only we can go for distillation.